Okay, so now what we're going to do is we're going to take this CSV file that is all of the squirrel data. It's notably the things that are going to go into our model are going to be things like predicting of the outcome. So what we're doing is, did the animal die or not? And the things that I think, that's kind of my prior guess as to what might be driving that, would be what life stage it was in, a categorization of injury, and then if there was season, as well as what life, as well as I think that was it. Okay. So what we're gonna do is I've now taken all of my data and I've reformatted it into the associated bins. And then what I have done is I'm going to pull that data in. So I'm going to open SPSS. And what I'm going to do is I'm going to import data and I'm going to import it as a CSV file. It's going to bring in, pull this over. It's going to bring in the squirrel data that I just had open. SPSS will read CSV files really easily, so it normally doesn't goof up any importing, but sometimes you might need to check if it's not saved in a weird way or if there's weird kind of characters in here that might throw off the comma separated values. It already imports it as a file. Oops. Oh, that was it importing. So it looks like this. It has all of the outcomes. So it tells you the name of that variable. It tells you that type of the variable. The type being the three that you can choose that you'll see commonly is mostly it's going to be strings, which are like a string in terms of this categorization is like a series of characters that aren't numbers. That's what all the string is. There's going to be numeric data, and then you may actually be using date data in here, but it's not going to be too terribly different from numeric data. It's just going to interpret them in a slightly different way. So numeric data as in weights, etc. Right? So you can change this if it has guessed the wrong one. You can put that in. Right? Most of it's going to be numeric or string data for our case. It gives a little bit more values about it. There's some ways that you can organize the data, but the other important thing is the measures at the end of it. The measures can come in three different flavors. They can either come in scale, which are 1, 2, 3, 4, 5, but including things like 1.1, 1.111, right? -5, right? So weight would be an example for scale because you can be 10 pounds just as easily as you can be 9.99999 pounds. So scale is ordered numbers, but there is the possibility to be between numbers, between like whole numbers. Ordinal data is similar to scale, but ordinal data is going to be data that is like first place, second place, third place, or mild infection, severe infection, no infection, right? So there's rankings in the like similar to like 10 pounds is more than 9.999 pounds. So there's rankings there, but unlike in scale data, ordinal data does not have any possibility to fall between categories, right? Between those bins. So you can't come in third point tooth place, right? You can't have somewhere between a body a body fat score. Like if you're using a body fat score of like 1 to 5, for like 1 is emaciated, 5 is obese. In that, you can't have a scale of 3.5. It has to fall on those ordinal values. That's where ordinal would end up. Nominal data is names or like the names of months. you have this disease or another disease. So that would be like the nominal data is going to be like, did you die? In this case, if it's died or not died, right? So that's the outcome for that nominal data. Now you can go in and look at the data, so just to make sure it imported appropriately, but you can see all of that data came in, and all of that data came out looking just fine. You can analyze the data if you want to do some like real quick descriptions of it. Things that you can do is you can just find, okay, I want to know what's going on with outcome. So partially you can do this to double check and make sure that you don't have something that's like you typed in a name wrong for something. So like I don't want to have like 3,000 squirrels that are alive and then one squirrel that's aliva, right? I've spelled aliva wrong or something. I want to double check my data to make sure that I've imported it correctly. So you can use descriptive statistics here. So you're going to analyze descriptive statistics into frequencies, right? You can describe things and get things like in descriptives, you can do things like what's the mean value or what's the standard deviation for this number, etc. You should go in and double check that before you do any kind of generalized linear model, that your data is following the assumptions that your model assumes, right? That if it's assuming that it's normally distributed data or it's binomially distributed data, right? So this is go do that if you are concerned about that. If you are just trying to get a quick peek at things, you can just dive right in. Or if you don't think that there's anything wrong, and you can do a cursory glance at the data to make sure it's not like super biased and has big problems with it, you can just jump in and immediately do a generalized linear model. This is nice because you get to analyze. You don't have to pick the GLM. You can do the generalized linear model in this, which is basically a more, it sounds silly, it's a more general version of that model, where if you go into the analyze code, you have to go into this one where it's a general linear model. You have to pick all of these. In a general one, it figures out which one you want. So it's just easier to do. The first thing that you need to do is you need to choose what type of model you are doing. If you are looking at an outcome, this is the thing that matters for the outcome. My outcome is binary. You could either be alive or dead at the end of this. So I'm going to choose the binary one. If you don't know the difference, you can choose between binary or probit. Generally, it's not going to matter too much. Generally, if you don't think there's weird stuff with your data, you generally choose the first one. Ordinal responses would be if I'm looking at like a body score, right? If I'm saying like, is this animal a scale of 1, 2, 3, 4, 5 in terms of fat on it? That would be ordinal data. If I'm looking at disease load, maybe I don't have like the exact number of eggs in a parasite that it has, but I know it's a heavy load or 0 parasites, low parasite load, or heavy parasite load. So I would be looking at something like ordinal response for that data, right? The scale responses would be the other ones that you'd want to do. And that would be like, if I'm trying to predict what weight an animal is going to be at release, I can use something like a scale data to try and do that prediction. Mine is binary. You either are alive or you're dead. So that's my type of model. The model that you are building predicts something, right? The outcome is the thing that is dependent on all of those independent variables. So for me, my outcome is my dependent variable. It's binary. It's either one or the other. You can choose the reference category, or you can just let us automatically assume it. It doesn't really matter for binary because it's just whatever the first one it interrupts, it walks into. I think it's set up to be last, which would be dead would be the reference category. If I switch it to this one, it would be alive because it's in first and second in alphabetical order. You don't really need to worry about that for the most part. Okay, now I have, okay, what the outcome is are you alive or dead? And then I need to find out what is a good way to figure out whether an animal is going to be alive or dead at the end of that care. So what I would want to do is I separate it into factors, which are all of the categorical data. So anything that is nominal or anything that is ordinal falls under categorical data, like factors. So for me, I made a month bin with just seasons. So I put seasons in here: spring, summer, fall, and winter. Life stage will be an example of one of these factors. You're either an infant, a juvenile, or an adult. You're not somewhere a split between the two. An injury type would be the one. I'm going to use their categorization of injury because I was looking at that a moment ago, and it seemed like a good way to do it and looked like a more specific way. So it says, hey, this is trauma or internal issues, or there's external parasites, or it died on arrival. So unsurprisingly, died on arrival is going to be pretty predictive of outcome. So maybe I actually shouldn't use that. Yeah, so what I'm going to use is I'm going to use injury, the one that I did, where I take like what put it into the hospital in the first place. I should probably not call this injury. I should probably call it reason for admittance. Oh, I can't have any spaces to admit. So I'll just do camel case. So now I've renamed the variable so that it actually is what it actually is. So now I have lots of individuals that I know why they brought in. I separated it into a couple bins when I was resorting this data in Excel. So what you can do is you can look at, if I want to find out what these bins are that I'm using, reason to admit. So now you can okay. So here on the bottom, if you can see this, I have 22% of my animals are attacked by cat. Another 29% are attacked by something else. Lots of them are dog, but some of them are other animals. A lot of animals, or sorry, I was reading the wrong percent. So not very many that were cat, not very many that were dog. A lot of orphans, some animals that were trapped, and some animals that were here because of trauma. A lot of those are like car accidents or getting run over by bikes and that kind of thing. So I'm not going to use categorization of injury. I'm going to use reason to admit as a factor. So now I'm going to see which of these factors might determine whether something dies or lives. My guess is that if something came in by cat, it's probably going to die because cats are rough on wildlife. And we could do, if I wanted to, I could do something like put weight in here as a covariate. The only reason I wouldn't put weight in here as a covariate, because covariates are linear values, so weight would be like a really good one to go in. The problem is weight is highly associated with life stage. So there's probably, if I actually think that weight is the big deal, or if I think life stage is the big deal, and I know that there's a lot of data that doesn't have weights but does have life stages in some of the older data. So I'd rather use the best data I have, and using both of them probably means that it's trying to compare the two, even though low weight individuals and infants are probably the same person or the same squirrel, right? So they probably shouldn't be using those. I could do something like what year it came into. I could put it in there if I wanted to, if I were to think that that'd be a reason to go in there, because that would still be a factor. But these are the ones I'm going to use. I'm going to see what this spits out. I have no idea what this is going to look like. So these are the factors that I'm going to use to build my model. And then I go to Model to build the model. I'm just going to hold down Shift and select everything and put them all in as main effects. If for any reason I think that there's different effects that are going to interact with each other, as in there's going to be some interaction between something, this would be, I think, if I'm making this scenario up, I think that monthly, the season that something came in or the life stage that something came in are drivers for whether it lives or dies. But I think that maybe there's some special relationship between the season and life stage. So like maybe if I get a bunch of infants in the winter, they're much more likely to die than infants in the spring. Right. So that would be like there's some interaction between the two things that I'd like to try and suss out. Generally, if you don't have a strong prediction for why that would happen, you shouldn't be looking at interactions because then you're just kind of fishing for statistical significance. So these are the ones that I think are good. I don't generally mess with any of this stuff. I use its estimation. I generally don't mess with any of this stuff. And then you can do things like EM means. This is a way to do comparisons between them. So if I want to see like life stages, if if one of them is worse off than another one, what I can do is I can compare adult to juvenile and juvenile to infant and infant to juvenile to try and look at those relationships to kind of help me understand what's going on in the data. So I pulled an EM means out for that. And now that model is done and it's going to spit out. This model, I wonder if I can zoom on this. Is that zoom? No. Is that zoom? No, none of these are zoom. So the way that this model works is, hey, here's that model I just ran. It's a binomial logit model. I included 6,000 some data points. Here's all those data points that I included. Some of them didn't have all of those, but it's going to be all the ones that I've used are going to be here. Then it's going to tell me things like goodness of fit. We don't particularly care about that for right now because I'm not comparing different models. If I were comparing different models of explaining why something is important, then I would want to compare their goodness of fit. Generally, I use AIC for like if I run this again and I decide to include gender, right? If I decide to include the biological sex of the squirrel as the driver for it, well, then maybe that might be a better model. So I would choose that as I would use the goodness of fit measure to compare those models. I only have one right now. Don't think that I should be running more. Generally, the test was significant. That's unsurprisingly that's the case because there's a lot of variables in there. One of them is going to be significant. It looks like all of them are significant. Wow. Okay. Model effects are all significant. So there is a significant difference in whether it came in the spring versus the summer versus the fall versus the winter. I don't know where that relationship is coming from because I didn't do the EM means for this one. I could go back in and redo it. You can this little box gives you like recently used ones, so you can do that there. And then reason to admit is also statistically significant. I can look at all of the degrees of significance here, but the important things to look at would be these EM means. So what this looks like is it looks like I had the reference value for this was dying. So it looks like 90% of adult squirrels come in and die. So this is actually like not what I would have expected. So if I ever find that kind of data that I'm like kind of confused by that I wasn't expecting to find, what I can do is I can go back in and I think it might be in descriptions. No. I can go back in and I can like reassign died and alive to a value. So I can say like alive is 1 and died is 0, and then that's still the same data. It's still binomial data, but sometimes it's easier when you have that. So let's just show how to do that. Let's recode into same variables. So what I'm going to do is I'm going to recode the outcome value, and then I have to give it new values. So if the old value was alive, I'm going to say the new value for this is going to be 1. And if the old value is dead, does it say dead or died? I think it's died. We'll just look. It is died. Okay. So I can say died is 0 and alive is 1. So now what it's going to do is it's going to recode that column. Every time it says died, it's going to put a 0. Every time it says alive, it's going to put a 1. And now it recodes it. It thinks for a little bit and says, okay, we're finished recoding. Now when I look at that data, it's going to fix it so that the outcomes are zeros and ones instead. So what I'll do is I'll just rerun that. I'm just going to rerun that same model again, so I don't actually have to do anything to do these comparisons, but it's all set up still the same way, so I don't have to change anything about the model. I'm just going to rerun it again so that it shows that new data. Oh yeah, well, okay, so now I'm looking at those EM means, and that's exactly what I thought it said, where only the 10% of my adult squirrels survive, which I was actually not expecting. I was actually kind of expecting infants to have the highest rate, but it looks like infants have the highest success rate. So it appears that if you're an adult that's come to the clinic, that's not necessarily saying that you are more likely to die than an infant on average. But if you're an adult squirrel that's come into the clinic, you're there because you're really messed up. Something's really wrong with you, which is why that you've shown up to the clinic. If you're an infant, you could have just fallen out of a nest, and so that's why you would be in the clinic. So probably the degree of injury is something that's driving this. So that might be a thing that I want to look at for other relationships. And I can look at the pairwise comparisons showing those comparisons as well. But this is a neat thing to see, and I can do. Maybe I'm just going to do all of these. Try and suss out what's going on in the data. So I can go down and look at my pairwise comparisons. So it looks like there's a moderately higher rate of survival in the spring. Surprise, surprise, that's when all the babies come. So if I'm saying that juveniles and infants are much more likely to survive, then that's saying that surprisingly when all the juveniles come, that's when the survival ticks up. And then it looks like animals that are brought in for trauma have the lowest outcome of survival. And animals that are brought in as orphans, so those infants with no injuries other than just that they fell out of a nest, are much more likely to survive at 33 or 37%. So this is showing me that I can predict about what an animal is whether it's going to survive or not. I can use all three of these as significant drivers for outcomes in that animal. So I have found 3 significant factors that are leading to death or survival once you've brought them into a clinic. So now from here, I'd write this up, make a graph that shows this kind of data, and be on my way. And that's how you use a generalized linear model. I learned something about squirrels today. Wasn't expecting it. Okay,